Okay, welcome everyone. Today we have Dömötör Pálvölgyi, from Budapest. Yeah, and he will be talking about C-P3O, orientation of convex sets, and other good covers.
Yeah, watch out. This is not C-3PO. Almost the same, but slightly different.
Sorry, C-P3O. Sorry.
Oh, I think I said it well.
Yeah.
Yeah. In fact, the first version, it was C-3PO, but then it made sense to name this mathematical notation. So sorry to all Star Wars fans. So thank you for the introduction. And I would like to thank Hong and everybody for inviting me. It's a great pleasure to be here or back here. 22 years ago, I've been in Tejon for the IMO, and now at least online, I'm visiting back. Okay, so I will talk about a new orientation of convex sets that we came up with. This is joint work with two of my students, Péter Ágoston and Gábor Damásdi, and with my frequent collaborator, Balázs Keszeg. So let's see what this is all about. First, I will define the order types of point sets. I'm sure that most of you are familiar with it, but let's just start from the beginning. So given a planar point set, we will assign to each triple of points Okay, so we assign for every triple an orientation in the following way that I look at if, like, let's say ABC, if they are oriented clockwise, then I give it a +1. If ABD are oriented ABD also clockwise, this also gets a +1. But ACD, here it gets a -1 because if I go for ACD, then it's oriented clockwise. Have I been saying clockwise? I mean, the others are counterclockwise, obviously. This is clockwise, so it gets a -1. And BCD is again +1. Among these 4 points, of course, you have exactly 4 triples. This describes their order type. And if you change, so I mean, a triple I can write in different ways, like ACD, I could have written it as ADC. And then the orientation becomes counterclockwise. So if you flip 2 things, then the orientation also flips. But if you do a rotation, like from ADC I go to CAD, then of course it doesn't change, it's still counterclockwise. Okay, so I'm sure that most of you are familiar with this order type orientation. And it's a classical result of Goodman and Pollack, who introduced this, that there are 2 to the 4 n log n possible order types on n points. So notice that this is significantly less than 2 to the 4 choose 3. So 4 choose 3 would be an assignment for every triple, +1 or -1, but most of these are not realizable as order types. So there are approximately as many order types on n points as n factorial or n factorial on the 4th power, something like that. No, not on the 4th power. Anyhow, it's n factorial to some power is the number of order types. Okay. So these order types, this orientation, we say that it's an orientation because it satisfies the cyclic property on the triples that I already talked about. And it also satisfies another thing that Knut called interiority condition. Oh yeah, sorry. And most often we study what some people call strict order types, which means that no 3 points are allowed to be collinear. If 3 points are collinear, then we would say that their orientation is 0. And the interiority condition is the following. If I have that 3 triples, these 3 are all oriented counterclockwise or clockwise, then this triple is also oriented clockwise or counterclockwise. So in the first figure, we had exactly this case. ABD is counterclockwise, BCD is counterclockwise, CAD is counterclockwise. Then if I tell you only this much, that already forces ABC to also be counterclockwise, no matter where D is. This condition holds for points, so for order types. Okay, so these are the things that I will use. This is some terminology. So when I talk about orientation or partial orientation, I mean that this condition is satisfied. When I talk about total orientations, I mean that you never can get a zero value. And if I don't just talk about orientations, but 3 orders, then I want that the interiority condition is also satisfied. So in short, a partial 3 order, I will just say P3O because I won't repeat all these conditions all the time. And the total 3 order, I just call it T3O, like total 3 order. So a P3O, you can imagine it as a hyperposet in a way. Just imagine in a poset, you have the smaller relation. And of course, if A is less than B, then you have that B is larger than A. This is similar to this condition. If you have a total linear ordering, then you must have that A is less than B or B is less than A if it's a total ordering. But of course, there's only one total order. We will see that these hyperposets are more interesting. And this reorder, this is like transitivity. If A is less than B and B is less than C, then A is less than C for posets. I'm just saying that all these 3 properties have an equivalent for normal posets for for posets. Okay, but unlike for posets, these T3Os can have a very rich structure. So if I tell you that I have a total order on n elements, then that's unique up to a relabeling of the elements. A T3O, on the other hand, can be a lot more complicated. We have seen that all the order types, the strict order types, belong to the T3Os. So these notions were introduced by Knut in '92 under the name interior triple systems, the T3Os. And he said that he wanted a better name. So we came up with a better name because we like this T3O a lot more, especially because we will look at many, many subclasses and we can't always say interior triple system. That's too long a thing. And this also highlights the similarity to posets. And some special subclasses of interior triple system have been studied a lot. Notably these on the right side. I already mentioned order types, but I'm sure that many of you have heard of oriented matroids or pseudo-line arrangement or these CC systems. All these 3 things are essentially equivalent to some level. And there's one more thing that has been studied, I think, only by Knut in his book called Axioms and Convex Hulls, which he calls interior transitivity. Anyhow, all these belong to this special group with interior transitivity. But today, we will look at a very different subset of T3Os and P3Os, which are derived from convex sets on the plane. So now I will give you an orientation for convex sets in the plane. So for any triple, we will define an orientation and they give rise to this new subclass. Okay, any questions so far? Good.
So as far as I remember, the one of the motivations of Knut was to do some sort of systematic study on this happy ending problem-ish.
Yeah, so at the beginning of the book, he claims that the motivation came from Voronoi diagrams, that they were discussing which point is closer to who or how would you do some Delaunay triangulation, because apparently he didn't know this whole thing. Okay. And then he started thinking about it. Then of course he found out from a colleague that all these are known, but still he went on and he developed this whole theory from some very simple rules or axioms. So these are what he calls CC systems.
I see. Yeah.
But I'm sure that to study happy end problems, you can also use these things. Okay, so let me go on. Let me give you my motivation. My motivation comes from weak epsilon nets. So a point set, a finite point set in some Euclidean space is called a weak epsilon net. If whenever you have a set in that space that contains a large fraction of those points, at least an epsilon fraction, then this net will intersect that set. No, I messed it up. Sorry. A net is a weak epsilon net for a finite point set. So this is also some finite point set. That whenever you have a C convex set, and that convex set contains a large fraction of this finite point set, then that convex set will be intersected by this net. Sorry, I messed up that definition the first time. Okay, and it's a classical result by Alon, Bárány, Füredi, Kleitman, and Lovász. These are two separate papers that for every finite point set, there is a weak epsilon net for these convex sets. And the first band was very weak. In the second paper, they had a better band. And for the plane, they could establish that it's like 1 over epsilon square. And later, general dimension was improved by this other group of people who proved that it's at most something like 1 over epsilon to the d. There are some polylogarithmic terms hidden there. And recently, Nathan Rubin had a breakthrough where he could improve the exponent with half more. Of course, if d is at least 2, then he could improve it. Already the planar case was a big breakthrough. And the very interesting thing is that from below, we know very, very little. The best construction is 1 over epsilon and some polylogarithmic factors. So these upper bounds are polynomial in 1 over epsilon, but the lower bound is practically linear in 1 over epsilon. So it would be very nice to close this gap. And I have to mention a result by Alon, Kalai, Matusek, and Mesulam, who showed that the fractional Helly theorem and some PQ theorems imply weak epsilon nets. So that's one way to derive weak epsilon nets. And they show that you can work in a very abstract setting without looking too much at the geometric structure. And there was a recent paper by Holmsen and Lee that showed that already some Radon property already implies that weak epsilon nets exist. But all these bounds show that epsilon nets exist, but the size of the epsilon nets is very bad. So yeah, so the size of the epsilon nets is not good, what you get from all these abstract methods. And the way that we want to improve, or I hope to improve on weak epsilon nets, is to get better PQ theorems, which I haven't told you yet what a PQ theorem is. They say that a family has the PQ property. Imagine like F is a family of convex sets. If from any P members of F, there are Q that intersect in a common point. Okay, so there is a point that's contained in all Q sets. For example, if P and Q are both D plus 1, then this is Helly's theorem for convex sets. Helly's theorem says that whenever you have D plus 1 convex sets, if you have a family of convex sets, and from any D plus 1, you can choose all D plus 1, so they have a common point, then all the family can be stepped by 1 point. Yeah, sorry, I didn't. Maybe I should have mentioned this in a later slide. So Helly's theorem says that there is one stepping point, and Hadwiger and Debrunner conjectured that in general, always there's a finite number of stepping points. And this was later proved by Alon and Kleitman. You need that Q is at least D plus 1. It's easy to see that if Q is less, then there might not be pierced with a bounded number of points, but otherwise it's always true. And then Helly's theorem says that 1 point is sufficient. And in general, there's a constant, but that grows very fast as P and D grow. We only have a very big bound that's like P to the D square. And as far as I know, this has not been improved ever since. If Q can go higher, then there's a result by Keller, Smorodinsky, and Tardos that shows that they could get a better bound, but only if Q is larger. If Q is D plus 1, then I think this is the best bound. And even special cases like D equals 2 means that we are in the plane. Yes, because if D is 2, then it means that any 3 have a point in common. So be careful that this D and this D, I mean, there's a shift of 1. Anyhow, so the first interesting case is this C4-2, which means that we are in the plane. And for convex sets, from any 4 convex sets, there are 3 that have a point in common. Then the original bound only gave 343. And this was improved to 13 by Kleitman-Gyárfás and Toth, and recently by McGuinness to 9. But the conjecture is that it's much, much lower, that is just 3. So I'm saying that that's the first step. It would be best to improve these bounds in the plane. So to get an improvement in the plane, we must look at the intersection structure of convex sets. And a first step is that at the cost of just one extra point, we can assume that the family that we want to stab, all members are pairwise intersecting. So any 2 convex sets intersect. I'm sure that many of you know the proof. I don't want to go into details. Just only remember that from now on, we can assume when we want to look at the structure of convex sets, that the convex sets are pairwise intersecting. Okay. Now let's look at convex sets that are pairwise intersecting, ABC. Either they have a point in common, and we can be happy because it means that they are easy to pierce, or they look like one of these things on the left or the right. It means that they intersect pairwise, but inside they have some empty region. We call this the hollow, although I won't use this word in this talk too much. But you can already see how to define an orientation. Either they go like this or like that. So depending on whether we are on the left or the right option, I will define an orientation. And here we are building on a paper that gave us this whole idea to look at this problem. There's a paper by Jobson, Casey, Leher, Pálvölgyi, and Toth, that if A, B, and C are pairwise intersecting convex sets that do not have a point in common, then if you take them away from the plane, then it will have one bounded component. This is what I called hollow in the previous slide. And around it, the boundary of this bounded region, you can go around it either like this or like that. So along the boundary, you will have a part of a boundary of A, a part of a boundary of B, a part of a boundary of C. So the boundary of this bounded region will have 3 components. And these 3 sets will appear there, either in clockwise or in counterclockwise order. And there's one more observation that we will use a lot. So whenever I refer to a lemma, I will mean this observation, that when you pick some points X, Y, and Z from the intersections, then this XYZ triangle will have the same orientation as this delta A, delta B, delta C. Okay, XYZ is the same as delta A, delta B, delta C. And no matter how you pick X, Y, and Z, it will be a constant. I mean, this orientation will be always the same. These are all easy observations. And then obviously we will define the orientation of such a convex triple as the orientation of X, Y, and Z. And if 3 convex sets happen to intersect, then we will say that the orientation is 0. Then we are in the non-strict case. But as I said, when we want to get PQ theorems, then we can assume that we are in the strict case, that this doesn't happen. Okay, so these are the possible orientations of convex sets. Any questions? Okay, then I hope that the definition was clear, because now we will work with this definition. So these are the 3 options. Whenever I talk of strict, then I only mean these 2. So when we are in the strict case, this is what I call a T3O. See, I keep on getting confused. And if it comes from a convex set, then it will be CT3O, but I don't know why I'm writing. I think it will be anyhow on a slide very soon. Okay, what are the simplest convex sets? Lines. So let's look at an example with lines. If you have 3 lines ABC, then this bounded region that they surround is this one. So here A, B, and C are like this. So their orientation is +1. And you might wonder when this orientation changes. A natural idea that we are used to, that when you make this Rademacher move, that you push the line A through this junction point here. So let's say I'm pushing A this way. if we push it to the other side, then what do we have? ABC. So you still have a +1. So surprisingly, the orientation doesn't change. If you push one line through the junction of two others, then the orientation does not change. So then when will the orientation of a triple of lines change? You have to start rotating one of the lines. Let's say I rotate A. Now it still hasn't changed. It's still +1. But if I rotate it a little more, then you see here I still have ABC. If you go around here, if you rotate it a little more, then you will have BAC as you go around. Okay, so for a triple of lines, the orientation changes when you rotate and when two lines become parallel. Before and after, they will have a different orientation with a third line. Okay, I hope this was a very enlightening example. And in fact, for lines, this notion has been studied by Goodman and Pollack, 38 years ago. They proved that if you look at this orientation of triples of lines, then if the lines are ordered according to their slopes in clockwise circular order, so if you look like here, you have A, B, C, D, according to slopes, then this order type will be the same as the orientation of some points that are ordered in counterclockwise. Okay, so here you have clockwise for the lines. For the points, you will have counterclockwise. And really, let's look at ABC. For example, that's +1. Here you will have A, B, and C. So it is also a clockwise orientation. Or if you look at ADE, that is clockwise. And also if you have ADE, so this triangle is also clockwise. This was not really a proper proof, but this is a very, very easy statement. You could prove it in 1 minute. Okay, so these are points in convex position. Now we have seen that they can be they give rise to some triple order, and that triple order can be always realized with lines. But what happens if you have points in non-convex position? Of course, if you have 4 points, then there's one configuration in non-convex position. And if you see, we can also realize this order type with 4 convex sets. So of course, for example, ABD is one here. And also if here you look at ABD, this will be this region that they enclose, it's also good. Or if you look at the outer ABC, that's obviously just the outer ABC here. That would be this big thing. Okay, so I give you an example that when you have 4 points and they give a rise to a 3 order, a T3O, that can be always realized by convex sets, by a C T3O. But this would be another realization. If you don't want to, before we had lines, here we had to introduce one non-line, but maybe a nicer picture would be to use only circles. So you have here ABD, or of course this ABC is also oriented well. Okay, I'm just giving many examples to make sure that everybody got the definition. I hope now that is really clear because we will work with this notion now. But in fact, I haven't really proved that this orientation that I defined on planar convex sets gives a 3 order. You remember what a 3 order was? We said that it must have this orientation property that is obviously true. If you that's just a permutation of the labels. There will be no problem, but there's also another condition, the interiority condition. As you have seen here, it was satisfied for 4 sets, but is it true in general? In this particular 4 sets, it was true, but is it always true that if these 3 are oriented like this, then the last triple is also oriented like this? Yes, indeed, it's true. That's why I can call it a triple order. And I proved to you the case by, so let's assume, if it is not 1, there are 2 options. Either it's 0 or -1. Let's assume that it's 0, so that ABC intersect. This figure that you have here is very wrong, but only because we are assumed something for a contradiction, and it's quite hard to draw an impossible figure. Nevertheless, we attempted it. Oh, maybe this is a very good point to mention that most of the figures were drawn by Peter and some by Gabor and Balázs, so I'm using mostly their figures, and they added some for the presentation, but I would like to them for the figures, and especially Peter, because he already had a presentation on this, so I reused many of his slides. Okay, just in the middle, a little acknowledgement, because I remember it now. So we are back to this case, and what I do is if A, B, C intersect, remember this means that A and B and C are intersecting, then I take a W point from their triple intersection. This W is drawn somewhere else because it's an impossible drawing. What's important is that A is from the intersection of A and D, B is from the intersection of B and D, C is from the intersection of those two. Now I use that lemma, if you remember, that I said that the orientation of this ABW triangle has to be the same as the orientation of this ABD triple set, so the same as this. This was that lemma that I told you we'll use frequently. Here I use that W is in the intersection of A and B. That's the property that I use. Oh, I also wrote it there. Okay. So because of that, we know that ABW is 1. We know that, sorry, we know this thing. This was a condition, and we'll know that then this is also 1. And similarly, I can do the same with BCW and CAW. So I get this condition, the interiority condition is true for these 4 points. But if it's true for the 4 points, then I can conclude that A, B, C are somewhere here, and that W must be inside them, because I know that for points, this is what the interiority means. So W must be in their convex hull, and if I know that W is in their convex hull, then W is also in D, because D was a convex set. And then this will contradict that the orientation of ABD is 1, because then ABD are intersecting, so ABD should be 0. And then that's a contradiction. Okay. So this was a very simple proof. I just wanted to show you that this lemma is indeed useful and we can prove things with it. Unfortunately, we couldn't prove the other case, and the orientation of ABC is -1. There we had to check a couple of cases to show that it's true, but I won't bore you with that. It's not so interesting at all. And anyhow, later we came up with a nicer proof for this as well. So just to put everything here in the diagram, now I have really established that these total 3 orders or partial orders that are derived from convex sets, remember I denote them with this C, it is indeed a 3 order, so it is a subfamily. But what I don't know is which of these containments are strict. I drew it like that this family is outside. And I also drew this rectangle to be bigger. But we haven't proved that, some of the rectangles are not contained in the others. So let's look at that question now. The most natural question is whether we can realize all point sets. So all order types, you can ask that, is this small rectangle inside here? Let's look at the point sets on 5 points, because we have already seen that any point set on 4 points is realizable with convex sets. And indeed here I show you that also on 5 points, they can be realized. We have already seen that if they are in convex position, then you can just do lines, or if you prefer this pentagon-like thing, oops. If you have 5 points like this, that E is somewhere in the middle, then also here, this ABCD, you can represent it with lines, and then you put an E somewhere here inside. You can check that it's good. For example, ABE will be ABE. So indeed, both are counterclockwise. And finally, there's one more 5-point order type on 5 points. That's non-degenerate. I mean, that no 3 are on a line. And also that we could realize. I don't know why this is like that. This is a C. As you can see, whenever D and D are inside the convex hull of A, B, and C, then if you draw A, B, and C as lines, then indeed all the interesting things happen inside here. We have a lemma that says that this is true, but I don't want to state it exactly now. Okay, so we have seen that all the order types on 5 points are realizable by convex sets. But interestingly, if you look at all these total 3 orders, you can enumerate that in total there are 6 of them. And the other 3 5-element T3Os, you can also realize with convex sets. But of course, they are not realizable by points. We know that there are exactly 3 point order types on 5 points. So there are all these 6 things. All 6 T3Os can be realized as C3TOs. So it looks like C-T3Os are quite powerful. But this doesn't answer whether all point order types are realizable with convex sets or not. I want to mention that instead of strict order types, if you look at partial order types, which means that we allow 3 points to be collinear, in that case, the orientation would be, of course, 0, then it's not too hard to find a counterexample. You just take a square and its center, these 5 points. This is not realizable with convex sets. So the partial question is much easier. Okay, not that easy. This is a 1-page proof. You have to check out some cases and make the appropriate definitions. I won't tell you the details of this proof. Mainly, I want to focus on what happens in the strict case. So when no 3 points can be collinear, then no 3 convex sets can have a point in common. Okay, here is a long list. There are 16 5-point order types, of course, from, oops, sorry, this should be 6. Of course, we just had the 5. This should be 6-point order types. There are 16 of them all together, and we could realize most of them with convex sets. There are still 2 that we couldn't realize, this and this. We conjecture that most likely they are not realizable as convex sets, but we are not sure. And the reason why we are not sure is that for a long time, we even had a proof that this is not realizable as convex sets, and then we did manage to find the realization. If you look at it, this realization is trickier than the other ones. Of course, here also you have 6 everywhere. Because at all the other places, this outside ABC, they can be picked to be half planes. And then all the inside things, they happen somewhere inside, all the interesting stuff. So we could prove that this configuration, you can't realize when A, B, and C are half planes. You see here, A needs to be a triangle or something. And then D, it needs to stab A through. Okay, so there you need some very special relations, but then you can realize even this. So that's why I don't dare to bet whether these other 2 are realizable or not. Most likely with a very long case analysis, one might be able to prove that they are not, but that wouldn't be such a nice proof. And anyhow, we wanted to go to some other direction. As I said, we were motivated when we started this study by PQ theorems and epsilon net, but we got really sidetracked this problem and we spent months trying to prove that there's a point time that's not realizable. And the answer is that indeed, there's a point set that's not realizable by convex sets. But we had to develop a lot of theory on the way, and it was a lot of fun. It's very fascinating. So let me share some of that with you. Sorry, any questions? Okay, now let me go on. See, I'm not that good on time. So let me define when a family of sets is called a good cover. It's when the intersection of any subfamily is either contractible or empty. An example is the family of convex sets. When you have some convex sets and you take the intersection of some, then the intersection will be either contractible or empty because it will be always convex. Okay, and I want to define an orientation on a good cover, on a family that's a good cover the same way. If the members are pairwise intersecting, then I can just do very similar things. So if you have some ABC, which might not be convex sets, you can see A goes in a silly way here. And you can prove that the orientation is well defined with some curves here. That's the left side. This took us like 1 page to prove, or even more, because we are very bad at topology. But I assume that somebody who knows topology could have proved this thing in 2 lines maybe. But anyhow, again, you can prove that this orientation is well defined. And we could also prove that it gives a P3O so that the interiority condition is satisfied. When there is some A, B, C, and there is some D that all has these right orientations with them. Like for example, BCD would be BCD. So you would have this thing for BCD. So the orientation is +1 for BCD. Then also the orientation of ABC is good. I won't give you the proof. Again, it uses some topology and other things, and it's not that interesting. Just take my word for it that they are indeed a P3O, even good covers. What you might see is that also here, when we had these big sets, I started to draw some smaller lines in them. And already here, these sets, instead of drawing sets, I just drew some curves, some sort of topological trees, because these sets, they need not be fat when you have a good cover. So this can also be a set, for example. And in fact, with this, you can capture all of these T3Os. Oh, sorry, I will call these good cover T3Os that are representable with these good covers. And I want to define these topological trees that showed up in this diagram. A topological tree is just a graph theoretic sense tree that is embedded in the plane. And if any two intersect in exactly one point, then they will form a good cover, right? If you have two trees that intersect, well, I can draw here instead of showing with my fingers. Let's say this is A, and I could do another color somehow, but doesn't matter. Let's say this is B. If they intersect in 2 points, then the A intersection B is not contractible. Okay, so this would be bad. But if any two trees intersect exactly in 1 point, then since 1 point is always contractible, then you get a good cover. And we could show that every T3O that comes from a good cover is realizable with topological trees. So don't be confused by this figure here. Not any two sets intersect. So this is not pairwise intersecting. This is just a picture from the proof. It shows the basic idea how we do. And also if I drew any two sets intersecting, then the picture would be very, very messy. So it's much nicer to draw this because our proof is a little more general. And you can see how we replace any set. Like let's say this middle red set, you just replace it with this red curve in the middle. That will become the topological tree that we associate to it. And as you can see, we can also allow one triple intersection, but just one for the proof to work, to be able to convert a GC3O into a 3 T3O. These that are representable by trees, I will call them 3 T3Os. And as I said, a proof only works if there's one triple intersection. If there's more, it doesn't work. So for the partial triple orientations, there is no equivalence. It's a simple example. You can think about it. Okay, so just to summarize these topological trees and these good covers, of course, any convex sets form a good cover. So this condition holds. And by the previous theorem, good cover, these total 3 orders are the same as the total 3 orders defined by trees by the previous theorem. So if you have a family of topological trees, now when we look at a T3TO, what will that know? Every member of the family is a tree, okay, like that. If you have 2 trees, then they will intersect in exactly 1 point. And if you have 3 trees, then they don't have a common intersection point. But if this is the 3rd tree, then they will close exactly 1 cycle. By cycle, I mean this graph theoretical cycle. I can't change the color. I'm too silly. Oh, no, I can't. Just the app is very slow. Okay. So this will be this graph theory sense cycle between their intersection points. Okay, let's go back to red before I forget. Okay, so from now, we will work with these topological trees. And here is an example, some topological trees. On the left, you see lines, because lines are, of course, also topological trees. As you can see, any 2 intersect once, any 3, for example, let's look at ABC. ABC will close this graph theoretical cycle. but they can behave in a more funny way. So now I'm representing, of course, this order type A, B, C, D. And this is also a good representation for that. Both are good representations. Here, I also have some topological trees, but somehow it's double winding here on the right side. If you see, for example, A, B, C, they will enclose this A, B, C. So it's still true that any three trees enclose a cycle, but now somehow if you go along all the way like A, B, C, D, then you wind around twice. I'm just saying that some funny things can happen when you look at these topological trees. Okay, any question about topological trees? Good, I hope still most of you are with me. So let me outline then our plan. We want to prove that this point, so there is an order type that's not realizable by topological trees. And because topological trees are the same as good covers, and good covers contain the convex set three orders, this will imply that there's also a point set that's not realizable as convex sets. So there's a point set order type that's not realizable by convex sets. So this will be our plan. But before we prove it for trees, we prove it for some simpler subclasses of trees. So let me introduce these. These are also easier to imagine. Okay, this is just an order type that I'm trying to realize as different subclasses of the trees. Oh, sorry, we have already seen that you can realize this by convex sets. This we had before. This is nothing new. With good covers, you can also realize it. Again, let's look at ABC. ABC is positive there. It's also, this is ABC, also positive here. ABC is, oh, it's just here. ABC is also positive here, this little thing. And now let's talk about trees. For example, when I say gamma, then I can have only curves when I have a gamma 3TO. If you want to look at ABC, you have it here, this little thing. It goes around like A, B, C. So it's also positive. And all the other triples are, of course, also fine. I just don't want to check every single one of them. Or we might have Y shapes. See, when I had gamma, then every tree was just a curve or a graph theoretic path. When I have gamma T3Os, then I allow one branching point. So on every topological tree, there's exactly one branching point of degree 3. So these are like the Y shapes. That's why we call it Y T3O. These are Y shapes. Again, let's find that ABC. It's of course here because this picture is almost the same as that one. And another important is this T3O, when every shape is a T line. Okay? When every tree is really like a T shape in the sense that it has a horizontal and the vertical part. Then again, let's find ABC. It's this little square. So again, the orientation is good. Okay, all these are subclasses of the three T3Os. And this 6-point order type, we could realize with all of them. There's only one exception with which we can't realize it with lines. As we realize with lines, we can only realize point sets in convex position. But with all these other subclasses, I could realize it. And now let's show you this big diagram. This is an extension of that earlier diagram that I showed with rectangles. Just here I have all these subclasses. Before we had this thing that was going down, and we had the convex sets. That was the first diagram. Here I introduced these good covers. I showed that they give the same T3Os as the topological trees. And there are all these subclasses that you could see, the Y shapes, the T shapes, the curves, and of course here are the lines. We already have seen that good covers and topological trees give the same T3Os. And we have seen that lines and points in convex positions give the same T3Os. And so we'll also see a characterization for T shapes. Okay. And that, oh, sorry, let's go back. Okay, not so much. So our plan will be to first show that these don't realize all point sets, then we'll show that these don't realize and that these don't realize all point sets. So this is what will happen. But first I want to talk a little about curves. Again, everywhere 5 should be 6. Surprisingly, with curves, we could realize almost everything. So if you look at the 6-point order types, you hope that with curves, it will be easy to show that you can't realize some things. I mean, we really hope that for this, there will be a simple proof with curves. But then, surprisingly, one day, by just doodling home, I managed to come up with this very beautiful construction. In fact, I remember when I was drawing, my daughter was so impressed that she said that, "Daddy, the solution is a flower." Because I was so happy I had to show everyone in the family what I managed to draw. And as you see, the other thing that we couldn't realize is also realizable with curves, but we couldn't do with convex sets. With curves, there's only one thing that we couldn't realize, but I'm not sure whether it's doable with curves or not. Anyhow, we could prove that there is some larger point set that you can do with curves. But the problem was that after that, we couldn't go on. So this containment, that this is not a subset of that we could do, but we didn't know how to go on to Y shapes from here. We didn't manage. So that's why we said, let's forget about curves. And instead, we started to focus on T shapes, because it turns out that T shapes are more similar to Y shapes than curves. So now I will show you this containment. This will be our next plan. So what are these T3Os? As I said, they are like T shapes. And some changes when you solve some 2 T shapes matter when you solve these vertical lines, but some do not matter. For example, if I solve D and E, so when I solve the bottom one with someone, that doesn't really matter. If you look, for example, here we had like D, E, F in this order. And if I swap these, still you have D, E, F in this order. So as I said, if you solve the bottom one with anyone, then you get the same T3O. And also if you solve the top 2 ones, something bad happened, okay. Even then you get the same thing. Okay, and because these T3Os are so nice, it's not hard to show that there isn't too many of them. So even by a basic counting argument, you get that there is a point set that's not realizable by a T3O. But T3Os are very nice that we could even give an equivalent characterization of those point sets that are realizable, whose order type is realizable as a T3O. So I have to define what a fast growing point set is. We say that a point set is fast growing if always when you take the next point, it will see the other points from below. I know this is not very clear, but I give you an example. But then, as I said, these 2 things will be the same, and these will not be the same, which you can see from some, you will see. Let me define these fast growing point sets. So let's say that we start with any point, and then you take another, so far no condition. But when you take the next point, that you will have to put somewhere below A and B. Like you can see why. So this already proves why these are almost the same as these T-shaped realizable point sets. Whenever I take a new point, I always put it below. So it should see everyone from below, and from which order it sees them. For example, F sees them as D, C, B, A. Then I will put F between D, C, B, A. And I have to put it so that these orientations are good. This is not a full proof, just rather to give you a feeling why these really feel like these should be the same. And I want to mention that these fast T3Os, not every point set is a fast one, but some point sets give rise to a T3O, to a fast T3O, when it's not obvious. For example, these 2 give rise to the same T3O. Just when you look at the right side, when you look at this, then you can't really tell that it's fast growing, but its T3O is realizable by a fast growing point set. Anyhow, this was not that crucial to understand. What the take home is that there's a point set order type that's not realizable by these T shapes. Okay, maybe I ask, are there any questions? Okay, I still hope that there are some people with me. And it's never too late to join in. For example, now there will be a very nice lemma that is not really related to the things that I talked to until now. So if you haven't been paying attention, this is a nice lemma to know. It says that whenever you have a finite point set, for example, P could be this point set, and no matter how somebody gives you a small number, you can always get a bigger point set such that if you pick a positive fraction of this point set, of this alpha fraction of this large point set, okay, I have some very big point set, P alpha, and I select a large fraction of their points, then there will be always some in this subset that give the same order type as P, okay? So P and Q prime give the same order type. So this is a statement that's independent of everything that I've talked about until now. We need this lemma, that's why I'm stating it. And its proof follows from a very hard machinery, from this multidimensional semi-ready theorem that says that whenever you have a large grid, I'm trying to draw a grid here, then you always have a subgrid in it. So whenever you want to find an n by n grid, sorry, now let me say it more slowly. For every n, there is a capital N such that if you select a positive fraction of an n by n grid, so S is a subset such that the size of S is at least C times n squared, then in S, you will have an n by n subgrid. That's the multidimensional semi-ready theorem. And because in a grid, you can find any point set, this automatically implies our lemma. But you don't have to use this heavy machinery. There's a very short proof. You can do this lemma in 2 lines with a nice trick. So I think this is a very good homework. You can hand it in for next week, those of you who are students. Okay, anyhow. So let's just accept that this lemma is true. And as a corollary, we have already seen that there's a point set that's not a T3O. And now using this, I can take a point set so that whenever you take a big part of that point set, that will not be a T3O. Why? Because in any big part, I can hide this small thing that was not a T3O. Okay, so now I have a point set that not just it's not a T3O, but it's very not a T3O, this P alpha. So this was the extra trick that we needed. And now with the help of this corollary, I can prove that also there's an order type that's not realizable by Y shapes. So why is this? The construction will be that I will take 3 points A, B, C, and I will put another point set, a very not T3O point set somewhere here inside this A, B, C. Okay. I think unfortunately this drawing will disappear when I turn the page, but it's okay. As I mentioned earlier, I didn't prove it, but I mentioned that because all these points are inside the convex hull of ABC, that will imply that all the interesting stuff, like the intersections, will happen inside ABC. So if you assume that this ABC and P16 has a realization as a YT3O, then it will be something like this. You have this A, B, C, all of them are Y shapes. And then inside you have some other Y shapes, and all the intersections that are important are inside this ABC. Like P1 and P2 intersect inside. Okay. And now we look at, okay, let's say that these P shapes, it will intersect B in some part, and we look at some sections of B, like this would be one section of B, another section of B, another section of B. I hope you see how I'm looking at different sections. And because I took so many points, there will be some Y shapes, some of these P ones that really intersect this B all in the same section. And I can even assume that all of them intersected from the same direction, which I really don't want to define. And then using this if I focus on only A and B, I can redraw these shapes nicely in a nicer way. Like I can imagine that these sections, this is just the appropriate section of A and B. They are like vertical lines. And that X and Y, these are the PIs, of course, that they will go between them in a nice way. And there's one more thing, that even this can't happen if A and B and C, and remember I took this P16 here, P64 here, if I put this P64 in a very flattened way, and the line of any 2 points intersects the AB segment, then this can't happen. Because if these intersect, that would mean like if you have X, Y, and A would have a different orientation as X, B, and Y. And if you have such a thing, then these 2 things have the same orientation. So even this can't happen, which means that these lines that connect A and B are different for every P. And because they are some Y shapes, they have some other thing going below or above from them. And these will give the intersections. And with a little more care, with a little more redrawing, you can show that in fact all these can assume to go down, or at least half of them. And then you are practically redrawing them as T shapes. Okay, so this was a bit hand-waving proof, but I think I'm really running out of time. But I claim that by now we have established that then for Y shapes, this is true. And now I want to finish the proof by showing that also for tree shapes, there's an order type that's not realizable, and that would finish everything because of these earlier sync containments. So as I said, for Y shapes, we have already seen there's a point set that's not realizable. And the main idea is that I put many, many points close to every single point that I had before. And I just want to rush through this last proof. And I will only keep a small fraction of these tree shapes that intersect the other trees in a nice way. And there's one more lemma that we use that's about some tangency graph. It builds on an earlier result by Ackerman, Kesseg, and myself that we had with a very similar proof about tangency graphs. So it was nice that we could also use that. And slowly, slowly, every tree shape we replace with a Y shape, and then we get a contradiction from this. I'm sorry, I don't have time to tell you more, but you can check our paper for the details. And just remember, now we have proved that I think most of these things are true. We didn't really prove everything, but I think that all of these containments can be shown to be really strict, and that there are no other containments. So like we can do things that is not true because these don't satisfy the so-called some other condition that CC systems satisfy. Okay, I don't know if I have time to talk more about things, or shall I stop? What's the policy? Now I made it smaller.
Yeah, take your time. I mean, it's fine.
There is no 1 hour deadline or something?
No.
Ah, okay.
That's right.
Then let me say a few more words about this. Okay.
Yeah, sure. Yeah. Go ahead.
So let's go back to convex sets, because this was that big detour that I wanted to show you that order types are not realizable. But in fact, we wanted to get some PQ theorems, right? So if we go back to 1 dimension, then if a family of intervals has the PQ property, which means that from any P intervals, there are 2 that intersect, then we can define an acyclic directed graph on the non-intersecting intervals, right? If I have a line, if I have 2 intervals on it, then I can just look at, one of them is to the right of the other. This will be my directed acyclic graph. Oops. It looks like this presenter also doesn't want me to go on. Okay, I don't know what happened there. Because we know that there is no chain of length P, a chain of length P would mean, many intervals after each other such that none of them intersect. So we know that we can't have a chain of length P. That means that any chain is of length at most P minus 1. But then in this poset, we can use Mirsky's theorem to get a decomposition into P minus 1 antichains. But what is an anti-chain? An anti-chain means that any two intervals in it intersect. But then I can use Helly's theorem in one dimension to get that all these intervals have a point in common. Okay. And because of that, I have a fitting set of P minus 1. So this proved the PQ theorem in one dimension. I know it's not very hard to get a PQ theorem in one dimension, but this is the main idea that we want to take over to convex sets in the plane. Remember that this was the orientation. Now we have an oriented three uniform hypergraph. So if there is a hyperedge, it means that the edges are not intersecting. If a hyperedge is missing, it means that they are intersecting. And we know that hypergraphs that come from convex sets, they satisfy the interiority condition and other properties because they come from convex sets. In fact, on 4 elements, they satisfy exactly one more condition that if they look like here is A, let's say A and B are almost the same, and you have some C and D, and if ACD doesn't have a point in common, then I claim that these orientations are the same. Okay, so this is the only other condition that the hypergraph on the 4 tuples needs to satisfy. And so this I could prove, but I don't want to because there isn't so much time. This follows from some nice, more general statement about convex sets and their orientations. I called it oriented colorful half Helly because you have like 3 groups of 2 sets, but you don't have conditions for transversals, but rather you take, oh, sorry, this is a shorthand notation. This means that these 3 intersect and these 3 intersect, or these 3 intersect, so any 3 intersect. Okay, this is a shorthand. So whenever you take 2 sets from one family and one from the third one, these will intersect. Then you get, and these are not intersecting, then you get that the orientations need to be the same. Like here, if A1 is the same as A2, this is a very cheap example, then all these orientations are the same. The proof is really short. You just take some X, Y, Z points from the intersections, and then you apply our favorite lemma to get that these are indeed the same. Okay, and remember, I wanted to look at the force-free property. That was the original motivation. And notice that the premise of the interiority condition already cannot hold if you have the force-free property, because then ABC would also be non-intersecting. But from any 4 convex sets, I need 3 that do intersect. And then our goal is to show that every hypergraph that satisfies these rules has a bounded chromatic number, because what does that mean? If a hypergraph has bounded chromatic number, it means that it can be covered by a bounded number of stable sets. And what does a stable set mean? It means that any triple is intersecting in it. But from Helly's theorem, we know that if any triple intersects, then all of the convex sets have a point in common. So this is our plan. But unfortunately, if you only look at the conditions on 4 elements, notably the hypergraph has the force-free property, that it doesn't have this thing, the premise of the interiority condition, and this last condition that I talked to you about. So these 3 conditions are not sufficient. We could find a counterexample that chi was still large. So the question is that what further conditions do we need? From the work of Holmsen and Lee, we know that most likely the colorful Helly is enough, but we would like to get better bounds. So we don't just want to get some bound on chi, but some reasonable small bound if you have the force-free property, like chi is at most 3 would be what we are after. Okay, so this was most of my talk. I wanted to mention some conjectures at the end, but you can look at it later if you wish. I will upload the presentation to my homepage, or you can look at the papers. So thank you for your attention.
All right, thank you very much. Does anyone have a question?